Hi, in this video, we want to take a look at self-organizing maps. We're going to be looking specifically at the Kohonen package in R. This is just one type of self-organizing map. This is from my internet research. This is by far the most common self-organizing map to use. So what I want you to take a look at right now is at this animation that's from Wikipedia. This is if you go to the self-organizing map page in Wikipedia, this animation will be on the right-hand side. All right, so what's going on is think of it as we're doing something similar to k-means clustering, but we go one at a time with each individual point. We assign a point to a cluster, and we go through and we update all of the cluster centers after that one point is given to its cluster. Then we take another point, and then we assign it to a cluster, and then we update all of the centers throughout. Now you'll notice that these points are not, these centers are not moving equally in the animation. What's going on is there's kind of like this weighted distance aspect, or weighted averaging going on. And so when a point is assigned to a cluster, all of the centers move, but the centers closer to that point move more than the other ones. And then it iterates through this process over and over and over until things don't really change very much. And then boom, we have our clustering. This is a very informative mapping system. It's visually very compelling. I'm impressed by the results that it gives, but unfortunately this takes a long time to run. So if you have a big data set, this may not be the way to go. Now, if you want to do the self-organizing map and you have a larger data set, one option that you could do is do dimension reduction, such as principal components. Just take a few of the principal components and then do the self-organizing map on your subset of principal components. And then you can go through and have your self-organizing map for a larger data set. All right, so now let's go ahead and take a look at this. I think that this Wikipedia page is definitely worth it for you guys to take a look and read. Just go through, read it. There's a lot of good information in this. Our textbook really does not have much in there. It's all correct. It's all accurate. I can see where it's going, but I don't find it to be a very informative aspect of the book. Overall, I do love that book. It's one of my favorite books. I go to sleep, reading it every night, but that particular section is not a highlight. All right, so let's go ahead and take a look at my R Markdown file that I made that help guide us through this. All right, so when we talk about self-organizing maps, by far the Kohonen clustering is the most common way to go, and that is the last name of the computer scientist or mathematician that came up with this, or is credited with coming up with this first. So it's very similar to k-means, except for after each point is assigned to a cluster, all of the centers are updated. The ones closer to that point get more movement than the others. Something that's kind of neat about this is that this system of clustering can handle both rectangular topology and hexagonal topology. According to the literature I read, hexagonal topology can handle corners of data better than rectangular topology. Now, what do they mean by corners? I don't actually know, but that's what I read, and I'm just going to repeat it to you. If you can see how it is, let me know. Go ahead and put a comment in the YouTube video. And the Kohonen package in R gives us a lot of ways to visualize the results. That's where I think that this has the most weight and the most compelling aspects of this clustering, is that we get a lot of pretty pictures out from this. All right, so let's go ahead and start looking through. So what we're going to do, we're going to take some NBA data, and we're going to get it, we're going to use the Hierarchical package, and we're going to use get URL and with GitHub, we're going to download a bunch of NBA player statistics. All right, so here what I'm doing, I'm taking read.csv, and to tell it where the path is, notice I'm saying text. The text is what I get when I put in rcurl get URL for this particular website. And now It is a CSV. It's comma separated value, so I'm putting separators of comma. There is a header on this data set. I'm checking names to be true because I want to make sure that everything's syntactically correct. And I do not want factors in here. I want character strings instead of factors. That's just good practice in R. Almost always, when you do read.csv, you don't want factors by default. What I do when I read a CSV, when I read a file in R, I don't let there be any factors, and then I manually go in and update the ones I want to be factors manually when alphabetical order is different from the order I actually want. So one thing I'll do sometimes, actually, when I load a CSV file, I'll put column classes, C-O-L capital C-L-A-S-S-E-S, column classes as all character, and then I'll go through and I'll change the character classes of the individual columns. For this data set, strings as factors is enough for us, so I just set that equal to false, boom, we're ready to go. All right, so something I did here was I set v numeric to all the columns that are numeric data. Oops, overshot that a little bit. So in this process, this type of clustering does not handle categorical data for us. If you absolutely have to do categorical data, then you need to do like dummy variables or categorical smoothing, which we'll talk about later. But for now, we're not even going to worry about it. We're just going to use numeric data. I recommend that you just, for this type of clustering and for k-means and for all the clusterings we've talked about, except for Gowers distance, is that you just don't use categorical data. But if your boss forces you to, use dummy variables for now. All right, so here, what we're doing is I'm just pulling out the numerics. All those, I want the numeric columns. So you'll notice that I'm taking the sapply function, I'm applying it to the MBA data set, I'm saying function class. And then, so this is gonna give me a vector. However many columns I have, I'm gonna have that many classes in a vector, and some of them will be numeric, some of them will be integer, some of them will be character, and so on. So, and logic will be the other one that we see. Since we're doing something with a clustering, I only want the numeric ones or the integers. I go ahead and just count the integers as a numeric variable for this problem, and then I go ahead and I get rid of the X column and the age. The X column is row numbers. I don't need it. Doesn't make sense for this problem. I throw it out. Age, when I was looking through before this video, I concluded that age was not relevant for what we were doing. So I went ahead and just threw it out. And then, as always, almost always, we rescale our data before we do clustering. The exception to that is when I do model-based clustering. All right, so now, here are all the columns I'm going to be working with. So when I did this v numeric, these are all the ones that came out. I went through before this video and I concluded that these ones here, the ones that are commented out, are really not that important for this problem, for this project. That these ones here are the most important. Now, something about this project is I know nothing about basketball. In high school, I did football, wrestling, track, rugby, and triathlon team. And you know what? I did nothing with the basketball the entire time. I have no idea what a lot of these are. I know what a three-point shot is and what a three-point shot attempt. This one, this dot, because of the syntactically correct aspect of R does not like percentage symbols. So R converted this dot to, or the percentage to a dot. Over here, R does not like to have leading numbers in column names. So what it did, it put X in front. So you'll notice every time that there's a number that would be leading, there's an X leading instead. So like here, this is field goal percentage, and this would have been 2-point percentage. Also, before this video, I took a look at the output and I concluded that there's kind of like 4 groups of variables, and I went ahead and grouped them together so that down the road, my clusterings look a little bit prettier, look a little bit nicer. which is a good practice to do before you show your boss your output. All right, so when we do this, just like with k-means, we're going to have some pseudo-random numbers going on. So I go ahead, I hit set seed, and I like to pick the number 823. Remember that is UCF on a telephone. And then the SOM, self-organizing map, is the function in the package to perform this. Now, you'll notice that in previous videos, I would do the package, then double colon, then the function. Here, I'm using the Kohonen package so much that I went ahead and loaded that good and early in the project. So like right off the bat, I loaded it. If I was only going to use like one function one time, then I would use the double colon notation. All right, let's get back to where we were. All right, so I'm doing self-organizing map. I'm taking those numeric variables that we already specified previously. Now, I also have position in the data set, and I'm going to use that as a target variable because that ends up being pretty interesting for this. Now, my grid is going to be a 3x3 grid, and it's going to be under the rectangular topology. And I need to use the self-organizing map grid function to organize it, and we're going to have 1,000 iterations. All right, playing around with this, I had trouble. There were plenty of times when I was just running different models to see how it performed that I had trouble with convergence. The larger your grid size, the more convergence can be an issue for you. Also, that will be true with if you have a larger data set. All right, so now let's go ahead and start plotting to see what things look like. Okay, so in this plot, what I'm doing, I'm taking the self-organizing map, and when I say changes, what's going on is I want to take a look, and I want to see how much movement am I having between iterations of the training process, and I want to see it flat. If I see that it's still sloped, then it hasn't converged, and I can't trust the results. And this is the mean distance to the closest unit. So this looks pretty flat. There were plenty of times when I was running this that it did not converge yet. I wasn't comfortable with it. A good rule of thumb is if you feel like you got a good model, run it at double the iterations. If you get the same results, you probably have something good. All right, now let's go ahead and plot the codes. All right, now this is where it starts getting more interesting. So here, remember, I have a 3x3 grid of clusters. I've got 9 clusters total. And I can look and see with these multivariate star plots, we can see that the different clusters have like different strengths and different weaknesses inside here. So up here, we can see that this group is good at the 3-point number of 3 points and number of 3 points attempted. And down here, these guys are better at the 2-point shots, field goals, PFs, and blocks. I don't know what PFs are. I'm sure one of you will tell me. Last semester when I taught this, my students knew off the top of their heads. They had to help me through the lecture the entire night. It was entertaining for them. All right, now for upcoming plot, I created a legend. Now, you'll notice I'm using the Viridis color palette. The Viridis color palette is a good choice because if you look through here, you'll notice that darkness, color along the rainbow, and intensity are all along the same continuum. And so that means that people who are colorblind tend to interpret this better. Also, if you think about the rainbow colors, yellow is smack dab in the middle. Yellow is a very intense color. So if I use that for plotting, people will mistake that the intense yellow is a more extreme value than it is when it's in the middle. All right, now here, let's go through. I'm just building a legend. Here, I took the legend and the position to define the color. And here we're doing the mapping. So here I'm coloring it by their position. All right, so check this out. I can see that I've got a bunch of, what is that? This teal is power forwards and centers in these two clusters. I can see that I have a lot more yellow, a lot of small forwards. And here we have a lot of point guards. And so we can kind of see that the positions group themselves up naturally. Now, last semester when I ran this model, I wasn't using R Markdown. I was showing this in class. I have full screen and I had more cluster centers to work with. It looked a lot more compelling then than it does now. Please, take the code, run this on your own data and try different, SOM grids. And if you have a larger data set, make it like really big, like maybe a 10 by 10, 100 by 100. You'll see that it gets pretty compelling. This is a good mapping system. All right, now let's plot the counts. All right, so what this tells me that this cluster has the most points, and then let's see, the darker ones have the fewest. So if I was looking to get rid of a cluster, I might want to get rid of one of these. So I might want to go with a 3 by 2, possibly, but with 40, I'm okay with that. All right, now we want to look at the distance to neighbors. And so that here we can see that this one has a lot of points in it and it's close to its closest neighbor. Well, this one is pretty far from its closest neighbor. Right? So if I have if a cluster is farther away from its closest neighbor, I'm more confident that I have good clustering. All right, now let's look at quality. And so here, the quality is lower. And remember, it's closer to other clusters than the other clusters that we have. So there's probably a few points here that may be able to go into other clusters reasonably. So kind of a way for us to check, do I have good clustering? All right, now another thing that this does is that this gives me, I can take each of my predictor variables and I can take a look at how those variables, the distribution of those variables are on the individual clusters. So here, I'm looking at the DRB, and the DRB was one of the more significant variables if we were to scroll up and look at the codes. Now, this scale is standard normal scale, because remember, I scaled the data before I ran this. And so I have to think of this as being like standard normal. 68% of the data is, between -1 and 1 usually. Because I subtract off the mean and I divide by the standard deviation. So here we've got some extreme values here, and we can see that this is close to 0, and we can see that this is negative, this is positive, and here's ORB. So this is like on the extreme positive side, and this is extreme negative. Now, something that'll happen if I have more data points, I have a bigger grid, I can see kind of a smoother transition as I go across and see that. If you look at the Wikipedia page, you have some good examples. If you get some data and you run like a bigger grid on this, you'll see like some really good, compelling pictures. Unfortunately, with a 3 by 3, doesn't really work out. I picked 3 by 3 just because R Markdown doesn't really display a more nuanced grid very well. Now here is for AST. See, there's really only one group that has a major value. And something that's nice also is that we can use hierarchical clustering off of this to give us like our clusters. So playing around previously, I decided, hey, looks like there's going to be 5 clusters, which is kind of a lot for a 3 by 3 grid. But when I had a more nuanced grid size, 5 looked to be a good fit. So I kept it at 5 for here. Please go through and maybe go like 10 by 10. You'll see that there's some good stuff in here. All right, so now that was rectangular topology. Now let's go into hexagonal topology. Now, if you don't know what topology is, if you've never, if you're not a mathematician, you've never suffered through this like I have, you don't need to worry about it. You just need to nod your head and know it's either a rectangle or it's a hexagonal system. That's it. I'm not going to test you on open sets. All right, so now I'm going to go ahead and I'm going to build a self-organizing map on the scaled NBA data with the predictors. And I'm going to go a 3x3 grid just because that fits our markdown well. And I'm going to do 1,000 iterations, hoping that that converges. So now let's go ahead and plot the changes. So I want to check, did this converge before I go any further? And it's nice and flat over here. So I feel like it converged. If I'm not confident, what I would do, I would run this again with 2,000 iterations. And if it looks like I get the same output, more or less pretty close to each other, then I probably have good clustering. All right, now let's look at the codes. All right, so this is very similar, except like previously when I had the rectangular topology, like these star plots were in the lower right-hand corner. And so they're in different positions, but I have very similar output. All right, let's look at the mapping. And so here I can take a look and see how things are going by their individual position. So here, this is blue. So this looks like there's a bunch of point guards in these two with shooting guards and small forwards also popping in. And then over here, this looks like centers and power forwards over here. When I ran it with a larger grid, it didn't look so Fruity Pebbles-like. It was more, the colors were more consistent, but I did have the centers and power forwards appearing together quite frequently. And I think it was, yeah, the two types of forwards were also clustering together frequently also. All right, let's look at the counts. All right, so we can see that yellow has a lot of players in it, while the purple has very few. So here, I'm actually not really feeling it on this plot because I don't have like a gradient of color. I would want to see something where it goes from like extreme value down to lower value as I move smoothly throughout the picture. Let's look at the distance. Remember, if I have greater distance between clusters, I'm more confident that I have good clustering. And here's the quality. So high quality here and here. We look back up here, that's probably going to correspond to distance. So I'm kind of surprised. Thought we'd have more extreme values for the ones with higher quality, but whatever. All right, now let's look at the individual predictors. And this was more impressive when I had more grids. Remember that this is on the standard normal scale because I rescaled. There's really only one cluster with a strong AST. So what one was that? That was the one that's covered up by the legend, if I remember correctly. Yeah, it's covered up, unfortunately. All right, now a nice feature about the Kohonen package is that in addition to giving us clustering, it also gives us a supervised learning model. So what it does is it takes your clusters and basically it does a voting system within each cluster. So if I have an observation, I pull it in, I see which cluster it goes into. What this package will do, it will take the points that were used in the training data set to like vote on what is a likely classification for that new point. And then what it's going to do, it's going to say, hey, my prediction is that whatever the vote was, that's my prediction. So it's a plurality vote. So let's go ahead and run through this. So remember, anytime I do supervised learning, I need to have a training set and a test set. Preferably, I have train, I have validation, I have test, but I was feeling lazy when I wrote up the notes, so I just did train and test. So the training set, we build the model on, build multiple models on. Validations, we use to check to see which model is the best one, and then the test set gives us our honest estimate on how the model will perform on new data. Now, and remember, my statistics on the training set should always be better than any of the others. So it'll be the training statistics will be the worst, validation will be the best, and tests will usually be in between. If I see that the training statistics are the worst, I usually have an outlier floating around. And remember that whenever I do this scheme, this like validation scheme for model selection, I am overly optimistic because I'm selecting the best among a bunch of models. The more models I have to choose from, the more like optimistic I'm getting because I'm kind of pushing that edge. All right, so here I'm just taking my data and I'm partitioning it into 50-50 train and test. I personally like 50-50 for my training and my test sets. I prefer to do it that way. And in this package, it doesn't want character strings for the target variable, so I convert them to a factor. And there's no inherent order on the position of basketball players, so I just leave it as is with alphabetical. So now this XYF function is how I actually train the model. So I put in the training data, I put in the target variable, I tell it what grid I want. So here I'm going hexagonal topology 3x3, 1,000 iterations for training it. And now I'm going to plot it. All right, now when I look at this, remember that you always have optimistic output on your training data set. Your training data set, it will always be like your best statistics. So I'm looking here, and I think I misspoke previously, so I want to retract what I said. Training data will always be the best data you have, then validation will be second, then test will be the worst in general. If you don't see that order, then be suspicious about something. You might have an outlier floating around. Now here we can see that the training data set is low, which is okay. Everything's flattened out. That's good. Now the codes plot, I'm not real sure how we're to interpret this. I think basically we don't want to see a pattern. We want it to look like random noise. And here is the voting on each of the clusters. All right, so here we can see that this cluster is going to vote power forward, and this one is going to vote small forward. This one's going to vote shooting guard for any point that is brought into this cluster. So if I have a new player, I have their statistics, but I don't have their position, then what I can do is like, hey, what position works for this guy? Let's go ahead and put it into the model, and we see, hey, they go into this cluster, then we'll say, hey, let's put them as a shooting guard. Now you'll notice that when we have very strong confident results, we only have one color going on. The bigger the slice of pie, the more confident the model is that that's what it is. Inside these clusters, it's kind of ambiguous. It's not really firm. It's not really confident about what it should be. And that's good to know, because in those cases, I can like double check. And in fact, I could run another model to classify these players if I want to be extra confident about the decision. All right, let's go ahead and do another plot. Let's plot the mapping. Let's see what that looks like. All right, so here we can see that with all the points, this is what it's classifying everything in this is going to be on the training set. Here, it couldn't really decide, so it just left it blank. It's like, I don't know, not gonna say. No information is better than bad information. And we have our counts. Remember, there was nothing in here. So we can see that there's a lot of points popping into here. Distance to neighbors. So, you know, these values aren't as big as I thought they would be. Quality of the plots. This isn't as big as I had hoped. And that looks like random noise to me. Now with the Q-tree function, I can go ahead and I can build a cluster or a clustering from the model. All I have to do is take the codes from the output from the supervised model, create a distance on it, put that in the H cluster, and then I can do a Q tree, you know, cut the tree into 5 clusters. Now, what this add boundaries does, add cluster boundaries, this goes through and this partitions my clusters into different groups so that I can it's easier to see which ones are similar to each other. And it goes through and clusters them in this manner. Now, this doesn't look nearly as cool as it does with a larger grid. Please, on your own time, go in, rerun this with more points in your grid. And we can check the mapping if we want. And we can make our predictions. The predict function works on the XYF map. And of course, we want to look at a confusion matrix whenever I do this. So I'm making a classification model. I want to look at the confusion matrix just to see what are the strengths and weaknesses of this model. All right, and I went ahead and I reordered the rows and columns so that we had larger values kind of grouped up. And we can see like centers are going along with these clusters more. And this is on the, if I remember correctly, this confusion matrix is on the training set. All right, that's on test. All right, so now that's all I got for you. I hope you found this interesting. Go through and play around with this. You'll see that the visualizations really are compelling if you take the time to run this on a larger data set with more grid points. Take care, and I hope you're staying healthy.